Let's take a closer look at instantaneous velocity and acceleration. So we have to look at what a derivative is. So the velocity of a displacement time graph is the slope of the line. But when the function gives us something that's curving, we can only find the slope at a given instant. And that slope is going to get closer and closer to what is the derivative of displacement and time. So for example, if we were to find the slope of this only based on the initial and final positions, we would get this line right here. But if we shrunk our time interval, then our line would get closer and closer and closer to the slope at that point. So if we choose a very small increment, that is what the derivative of x is. And if we pick a very small increment of time, that's what the derivative of time is. As these approach zero, we get closer and closer to the slope of the line at that point. So what is instantaneous velocity? As the limit of t approaches zero for x and t, we get closer and closer to the instantaneous velocity, which is dx over dt. So what's the slope? The slope is dx over dt, which is v inst. We can look at the same thing for acceleration. If this is a velocity time graph, in this case we want to know the slope, and the slope is equal to v over t, which would be acceleration. So the closer we get, this is an approximation that's bad, but as we get closer and closer to this line, as v gets smaller, dv, and as t gets smaller, dt, we approach the point where the slope is equal to the exact acceleration at that moment in time. So that's the limit as t approaches zero of delta v over delta t. So what is that? That is dv over dt. So we can say the slope is dv over dt, or we could also say it's the second derivative of displacement. So that would be a inst. So let's look at change in velocity and change in position. These are going to be integrals. Working backwards, the area under this curve is going to be equal to the change in velocity. So what is an integral? An integral is taking all of these little slivers, which are going to be dt's, and summing them up. That's what an integral is. So when we say an integral, this comes from basically the Roman s. This is the summation. What is it the summation of? Of all of the acceleration function for all of these little dt's. It's finding the area. And what are we doing that from? We have bounds. We're doing it from t1 to t2. Now, the same thing is happening when we do change in position. Change in position is going to be the area under a velocity time graph. So this is going to be our delta x. So again, we're going to sum up all the dt's, do our summation for all these little tiny derivatives of time, and that's going to be equal to the integral of velocity with respect to time, and we're doing that from t1 to t2. So the integral of acceleration can find us the change in velocity for a function in which it's changing. But what happens if the acceleration is constant and we integrate? Well, let's take a look at this. We're going to have v is equal to the integral from 0 to t. We'll start at t equals 0 to make this simple. And we're going to say a dt. Well, if a is constant, we can pull it out of the integral sign. So that's going to become a integral of dt. Now, this gets confusing for a lot of students because what are you integrating on? I mean, there's nothing here. Well, in essence, you have the number 1. But it's integrating on time. So what time is equal to 1? Well, it would be t to the 0. T to the 0 is 1. So now when we apply our power rule, we add 1 to the exponent. 0 plus 1 gives us 1. Divide by the new exponent, 1. So that just becomes t. So we have v is equal to at from 0 to t. And whenever we do an integral, if you've learned this in calculus, you have to add a constant. Now, in most cases, the constant ends up being 0, but not always. Well, what is the constant when we're dealing with velocity? What constant do we begin with? That would be our initial velocity. So at minus a0 would just be at. So what does this become? This becomes our constant initial velocity plus at. And this is the velocity at a moment in time. So what's that velocity at time t? That would be our final velocity. So this formula works only when the acceleration is constant. But what if we do this integral on the formula we just derived? In other words, we take x and do the integral on velocity with respect to time from 0 to t. Well, in that case, if we sub in v0 plus at, we'll have v0 plus at, all of which is with respect to time, from 0 to t. Now, we can actually break this integral up, and we can say that this would be the integral of v0 dt plus the integral of at dt, and integrate them separately. Both of these would be from 0 to t. Well, this initial velocity is a constant, just as we saw before. It was our plus c. So we can pull that out of our integral. And acceleration is constant because we're doing this for a constant acceleration situation. So that becomes at 0 to t. T is not a constant. T is changing. So when we do the integral of 1 dt, that becomes t. So that's v0 t from 0 to t, plus integrate t, that's t to the 1. 1 plus 1 is 2. Divide by the new exponent. That becomes 1/2 t squared, or we can write that as 1/2 at squared from 0 to t, plus our constant c. Well, what's our constant for position? That would be the position that we start at. So we could rewrite this as our constant, x0, and then v0 t minus 0 would just be v0 t, and 1/2 at squared from 0 to t would just be 1/2 at squared minus 0, so that would be 1/2 at squared. Now, this is our initial position, so x here is our final position. So if we subtract them, we have x final minus x initial equals v0 t plus 1/2 at squared. We can replace this with just x, which would be our displacement, or we could say delta x to reinforce the idea that this is the change in position. Finally, we could take this formula, vf equals v0 plus at, and do an algebraic substitution with x equals x0 plus v0 t plus 1/2 at squared. Now, I'm not going to do this derivation. It takes about a page. But the main thing that you need to know to take away from this is that you end up with vf squared equals v0 squared plus 2a delta x. And what's important here is the relationship between these. So if everything else is a constant, the v0, the 2, and the a, we could say that delta x is directly proportional, delta x is directly proportional to vf squared. So if we were to graph v and x, that would give us an exponential graph. We've done many problems in which we've looked at things moving horizontally that are accelerating, but the most popular types of questions dealing with vertical acceleration deal with falling objects. Now, when we talk about a falling object, everybody thinks of an object that's falling down, but technically when an object is thrown up into the air, it's also falling. It's in the act of slowing down. It is accelerating in the downward direction. So, in the absence of air resistance, falling objects near the surface of the Earth have a constant acceleration of 9.8 meters per second squared down. Now, why is that? We talked about net forces. So, the force on a falling object is Fg. This is called its weight. If there's only one force acting on an object, that is its net force. If the net force is down, then the acceleration has to be down. That doesn't matter if the object is moving up, if it's at the top, or if it's on the way down. The entire time, the force is down. Therefore, the acceleration is down. So if you take a ball and you throw it up in the air, and it moves up and it comes back down, on the way up, the ball has a net force down. So if we're going to call up to be positive and down to be negative, that net force is negative, and the acceleration has to be the same as the net force. So the acceleration is negative. But the ball is moving up, so the ball has an upward velocity. What do we know from the last video about what happens when the velocity and acceleration are in opposite directions? Well, what happens is the object slows down. And that makes sense. If we throw a ball up, we would expect it to slow down on the way up. At the top, it may seem like it's not accelerating, but there's still a net force. Gravity is still acting on it down, so it's still in the act of accelerating. It's still in the act of changing its velocity, even though its velocity is 0 at the top. So at the top, it has stopped. On the way down, the net force is still down. Notice, the net force is down the whole time because the force of gravity is down the whole time. So we have a downward net force, therefore we have a downward acceleration, and we have a downward velocity because it's moving down. What is true when the acceleration and the velocity are in the same direction? The object speeds up. We could have done this entire problem again by flipping the signs, and flipping the signs would have given us the same final result: slows down, stopped, and speed up, even though these would all be opposite of what they are now. And finally, something else we need to pay close attention to is the sign of displacement. Let's say a ball is thrown up from the edge of a cliff. It goes up and it comes back down. If we choose the start of the problem here as our origin, then that's 0. Well, remember that these formulas are working off of displacement, and displacement is the start to finish distance. So it starts here, it ends here. So if we call down to be negative, we have to make our displacement negative. Let's solve a problem. We have a ball that is tossed straight up at 19.6 meters per second. So it's thrown up, and I'm going to call up to be positive. The question is, how high does it go? And also, how long is it in flight for? So I'm going to call this an up trip. That's going to be the time it takes to get to its max height. So our initial velocity is 19.6 meters per second. Its acceleration is down. We're calling down negative. That's the direction of the net force. The final velocity is when it gets to the peak. How fast is it going when it gets to the top? 0 meters per second. And we want to know how high it goes, so we're looking for delta x. So VF, A, V naught, and delta x. Our easiest way to go is VF squared equals V naught squared plus 2A delta x. And subbing in the numbers, that drops to 0. So we have 19.6 squared plus 2 times negative 9.8 times delta x. And when you do the math on that, you end up with a delta x of 19.6 meters, not meters per second. That was the velocity. Notice that this answer came out positive, which tells us it's up. Its displacement is up. Now, how long is it in flight? Well, we could do this as an up trip and then double the time, or we could solve this as a total trip and find the time in just one step. So it leaves the ground with an initial velocity of 19.6 meters per second. It comes back down at 19.6 meters per second in the down direction. So our final velocity is negative 19.6 meters per second. The acceleration is down the entire time, so that's negative 9.8 meters per second squared. And the time is what we're looking for. So in one step, we can do VF equals V naught plus AT and say negative 19.6 equals positive 19.6 plus a negative 9.8 times t. And when you subtract that over and divide by the negative 9.8, you get a positive 4 seconds. If you do get a negative time when you're doing any of these, you've made a mistake. So let's look at what a graph of this would look like. Well, at the beginning of the position, it's going very fast, so the line will be steep. And as it slows down, the slope decreases until it reaches its maximum value, and then it starts to increase on the other side. So there's our maximum displacement, and the slope of the line starts as 19.6, decreases until it gets to the top where the value is 0. That's the point at which it stops. Then on the way down, the slope gets steeper and steeper, meaning the velocity is increasing, but it's negative, meaning it's speeding up in the downward direction. And this makes sense. So what about the velocity? The velocity starts as positive 19.6 and slows down 9.8 meters per second every second. And it's going to decrease until it gets to the top. That's when it's at the top, when its velocity is 0. And then it's going to increase until it is going 19.6 meters per second downward. This is where it gets back to the person's hand. And the acceleration, we know, is downwards the entire time. So that's a constant 9.8 meters per second squared. Let's do one last problem here with throwing things. So we have a ball that's thrown straight up at 19.6 meters per second, but it doesn't come back down in the person's hand. It continues to fall off of a cliff and lands 100 meters down below. The final velocity is not going to be 0. I see this as a common mistake that people make. The final velocity is how fast it's moving the moment before it hits the ground. So let's do this as a total trip, and we'll call up to be positive, down to be negative, and we're trying to find the time. So we know the initial velocity is 19.6 meters per second. That's up. The acceleration is in the direction of the net force, which is down, so that's negative 9.8 meters per second squared. The displacement is down from the origin of the problem, so that's negative 100 meters. And we're looking for time, and we also don't have the final velocity. So we could do this like this. Delta x equals v naught t plus 1/2 at squared. But you'll see there's a problem. We have negative 100, 19.6 times t plus 1/2 9.8 times t squared. If we rearrange this and bring the 100 over, whoops, that's negative, and bring this over to the front, half of 9.8 is 4.9. Then we would have 0 minus 4.9 t squared plus 19.6 t plus 100. That's a quadratic equation. So we're not going to do it this way. I'm going to show you how to do it without a quadratic equation in 2 steps. But if you were to solve this with the quadratic equation, you would end up with 2 times. One would be negative and one would be positive, and you would choose the positive answer. The positive answer is the time for it to do this. The negative answer would be the time it would take to go backwards in time to complete the rest of the other half of the parabola. So to do it in one step, we can do Vf squared equals V naught squared plus 2a delta x to find the final velocity. So that would be Vf squared equals 19.6 squared plus 2 times negative 9.8 times our delta x, which is minus 100. And if you do the math on that, you get Vf equals 48.4 meters per second. But we've got something we have to be careful of, because to solve this, we did the square root of Vf. Well, the square root of a number gives us 2 answers, plus or minus. So really, we have plus or minus 48.4. And we know that the ball is moving down, so our final answer has to be negative. Finally, we can apply Vf equals V naught plus AT and put in our minus 48.4 and our positive 19.6, that's our upward velocity, plus negative 9.8 times t, and t comes out to 6.9 seconds. Let's say we have a rock that's thrown straight up at 30 meters per second. It rises to the top and comes back down. It travels a total height of 45.9 meters. And the question is, how fast is it moving at 2 seconds? So the easiest way to do this, we have to choose our directions. I'll call up positive, down negative, is Vf equals V naught plus AT. So we can say that the initial velocity is 30 plus negative 9.8 times 2, and our final velocity comes out to 10.4 meters per second. The second question is, how fast is it moving at 4 seconds? Well, we can do the same thing. We can say Vf is equal to 30 plus negative 9.8 times 4. And when you do that, you end up with negative 9.2 meters per second. And the reason I wanted to do this problem was just to illustrate something, which is, if we find the velocity after a certain amount of time for this object that's traveling in a parabola, it's moving up with plus 10.4, so it's on the up trip. This velocity came out negative, which means the ball's on its way back down. All right, here's a question with an added trick thrown in. It's a ball that's on the top of a cliff and it's dropped. But there's a second ball that is thrown straight down with an initial velocity. And we don't know what this initial velocity is. But they tell us that they hit the ground at the same time. So again, we have a ball that's dropped and a ball that's thrown straight down, and they hit at the same time. And the question is, what is the initial velocity of the ball that was thrown straight down? So let's just start by finding out how long it takes the ball, or I said it was a stone, stone 1 to fall the 43.9 meters. So we can do that easily with x equals v naught t plus 1/2 at squared, because this one's dropped. So the initial velocity gives us 0 in the first term. So we call, I didn't choose that, up plus, down minus, so that's minus 43.9 equals 1/2 negative 9.8 times t squared, and that means that t is going to come out to approximately 3 seconds. So for stone 2, now we know the time, because stone 2 was thrown down 1 second later but hit the ground at the same time. So for stone 2, it only took 2 seconds. So now we can use the same formula, except we now know the time. So it's minus 43.9 meters equals initial velocity, that's our unknown, times t, which is 2 seconds, plus 1/2 negative 9.8 times 2 seconds squared. And that comes out to negative 12.2 meters per second. So this question, I'm going to show you how to do it with a trick. The question has a car that's starting from rest and accelerating at 5 meters per second squared. So it's speeding up, speeding up, speeding up, speeding up. And at the same time, there's another car that's traveling at a constant velocity of 20 meters per second. And the question is, where do they meet? We can do this with relative motion. So rather than say that this car is accelerating this way and this car is moving at a constant velocity this way, what we're going to do is say that this car is parked and take its velocity and add it to the velocity of this car. So we can say that this car is moving 200 meters towards a parked car, not from rest, but from the velocity that this car has. So we're going to take its velocity and add it to this car. And that's exactly the same problem. So to do this, to find out where they meet, we can first find out how fast this car is going before it crashes into this other car. And the easiest way to do that is with VF squared. So we can put in our numbers, which are going to be 20 squared plus 2 times 5 times 200. And that gives us a VF of 49 meters per second. So now, since we know the final velocity, we can get the time before it crashes into it. So that would be AT. So we say 49 meters per second equals 20 plus 5 times t. And t comes out to 5.8 seconds. So that's how long it would take for this car to crash into this car if this was still and we added its 20 meters per second to this. But that time is exactly the same as if this car was moving at 20 meters per second and this car was accelerating from rest at 5 meters per second squared. So now, how far does it go? Well, let's go back to letting them both move. So now we can say delta x is equal to v naught t plus 1/2 at squared. So it starts from rest. So we're looking for the displacement, and that's going to be 1/2 5 times 5.8 squared, and that's going to give us a displacement of 84 meters. But just to check the math on this, so it goes 84 meters. How far must this car go? Well, to add up to 200, that would have to be 116 meters. But let's check our math. So if we do v equals x over t, we can say it's moving 20 meters per second for 5.8 seconds, and 20 times 5.8 is 116 meters.